this is the third part of the lecture. It's about heterotic model building as suggested. I wanted to do. So before, maybe think of where the name comes from. Okay? Why not just erotic string? Why is it heterotic? And it's a technical term that it comes actually from genetics or even agriculture, that you try to mix two species to get a stronger one. And well, like crossbred means you mix two. And then here you are mixing, like Narayan, you are mixing the fermionic string with the open string to get something that is better, or it has other properties, which is the heterotic string. So, Daniel está ahí. ¿Cómo se puede poner?
Escape para que se cierre un poquito. Escape.
Escape. Yes, so the heterotic string. Okay. So the main idea then is that on the worksheet, the degrees of freedom for the right sector and the left sector are different. Okay. Maybe I will use different notation as Narayan. I mean, for me, the right sector is the Nevet-Schwarz-Ramon sector, where the degrees of freedom are the usual ones of the fermionic string in 10 dimensions. So you have some right-handed coordinates and some right-handed fermions. These are fermions on the worksheet in 2 dimensions. But this index here is also vector. Now, in the left sector, you are going to do something else. You keep the coordinates, the left and they pair with this to give you some geometric interpretation. But then there are some other degrees of freedom. Okay? That, in the case that I explained to you, they are 16 bosons. Okay? 16 bosons that must be compactified in some special lattice. And also, as he was explaining yesterday, this is the origin of the gauge symmetry in the heterotic string. Okay? It's like kind of enhancement, and then you get extra gauge bosons. But there is another formulation in which, instead of having the 16 bosons, you have 32 fermions. There is a property in 2 dimensions that is called bosonization. That it means you can, instead of using fermions, you can use bosons. And it's for 2 bosons, for 2 fermions, you can make them complex, and they will correspond to one real boson. Okay? So instead of 16 real bosons, you can have 32 real fermions. Okay? And one can show that in this construction, if you include all the Nevet-Schwarz and Ramon sectors. Now, if these are 2-dimensional fermions, you also have to consider Nevet-Schwarz and Ramon sectors. That, I mean, this kind of boundary conditions for these fermions also, just like you did for the fermions in the fermionic string. Okay? Now, if you consider all these boundary conditions or string structures in the partition function, then this is something that is going to give you a modular invariant partition. Okay. Yes. So I'm going to use this formulation. I decided to use it because I didn't know that I was going to do the bosonic. Okay. And also because I thought with the things that you have learned during the school, maybe this would be easier to understand. At least to understand how you compute the spectrum and so on. Maybe I'm wrong, but now I have prepared this way, and I will do it this way. Okay? So, for instance, this is what you have, and what you have to do now is to find all the oscillator mode expansions and so on, like you have done. You have done it here. You have done it for the excess for sure, for the recurring string, and to carbon digit also for the fermions. And then you will have the oscillators alpha for the excess, the oscillators B and D for the fermions. And you will have something similar to B and D for the lasses. Okay, for this fermionic new degree. So for instance, let's compute the massless states. Okay? A few, not all, because I'm not going to do it. Okay? And then I have to look at the right sector and the left sector, and the states are these tensor formulas. And I need these mass formulas. I call them mass formulas. So Narayan, or people will call them L0, L0 tilde, and so on. I call them mass formulas. These are things that have the occupation numbers, these numbers, n's, and they include here the normal ordering. Okay? So then I'm going to do here just a bit of what is written here is in the Neve-Schwarz. Okay, this is Neve-Schwarz for this and Neve-Schwarz for the lambda. Okay, and an exercise for you is to okay. For this you have seen in the right sector where there is the side. In the Neve-Schwarz, the normal ordering is this -1. Okay, an exercise for you computed in the Neve-Schwarz of this now for the lambdas and show that this is -1. Okay? And now let's look for the massless states. Well, in the right sector, you know already. Okay? You have this in the Neve-Schwarz, you have this kind of massless states. Okay? In the left sector, what can you have now? Okay? Well, these are also fermions like its size. Okay? But you need n equals n lambda, the occupation number of the lambdas to be 1, to be massless. So you need 2 lambdas. Okay? And precisely, well, 2 lambdas with this model, -1/2, and 1/2 plus 1/2 is 1, and these are the massless states. Okay? Now, what are they? How many are there? Okay. Well, this A and B go from 1 to 32, and this is antisymmetric. These are fermions that they commute. And if you count, there will be 32 times 31 divided by 2, and this number is 496. Okay? And this happens to be the dimension of the adjoint representation of SO32. And well, one can show in more detail using conformative theory and so on that indeed these are gauge vectors. I mean, this will give you precisely the adjoint of SO32. So what we are getting here, I call them gauge vectors because I mean the space-time what is telling you that they are vectors in this index. Here is like cone, but when you go back to full, this is the vector index. Okay, so this is one example of a massless state. Now here in this Neve-Schwarz, there is one more. You can tell me which one it is. There is one here, an additional state in this set. Can you see which one it is? Well, a hint is something else that you can saturate here the one. How can you saturate here the one? With the oscillator. Okay. Well, the other state will be you there. The other state still the right part is this, but the left part it will just be some usual oscillators coming from the X. Okay. And this is all you will. This is all. Okay. Can you see this? So what are we going to get? And then, okay, I can look also at what happens in Ramon times Neve Schwartz. Again, I mean Ramon for this, Neve Schwartz for this. Okay. And I would also have to look at Neve Schwartz, Ramon, or Ramon, Ramon. Exercise for you to show that in these sectors there are no massless states. Okay. Because of the normal orderings, you will find there are no massless states. So all massless states will come from Schwartz, or Ramon Schwartz. Okay? And so what are we then getting? Okay. This state I will denote it as like a vector. And the A vector is this. And the 1 is because it does not transform in this esothericity. The state doesn't have any lambdas. Okay? So it's singlet of the esothericity. And then I have these, the ones that are written there. This I will call A vector. Represent that representation. And then you have the same things where here you replace this A vector with the A inner of the Ramon sector. Okay? And then you have to do every, let me see, maybe I'm confused now with the, sorry, yes. Okay.
Sorry.
Sorry, I mean, I'm sorry. These are, I wanted to do this part. This one I call A vector 1. And this part I call it like this is the and then for the right, this is the A vector on the right. And this is also a vector, but this on the left. So this is acting on the left. And this is also a vector. And then here you can also have these spinors from the Ramon sector. Okay? So if I didn't manage to confuse you, what I get then will be something like from the right sector, I get this A vector, this one, and the spinors from Ramon. Okay? And they are all singlets under the gauge part. So the gauge part I put here in blue. And then from the right sector, I get these ones. I mean, left sector, I get these ones. And I do the product in the usual way. And then, again, when you take this A vector with these ones, you get the dilaton, the metric, and the symmetric tensor. And when you do the vector with the spinor, you get the gravitino and another field called dilatino. So this is something also you get in the fermionic string. But in the fermionic string, if you remember, I mean, this was another fermionic oscillator. So it's a bit different, but this sector is universal. It's in the heterotic, it's also in the type 2 strings. Okay. Here the new thing that will be these ones here, the ones that are charged, okay, that have this gauge degrees of freedom. And they are, I mean, with the vectors, there will be gauge vectors, and with the spinors, there will be the gauginos of the group. Okay? So this is the matter content now of 10-dimensional n=1 supergravity coupled to Young Mills. Okay? And it's Young Mills with, in this case, example I have done with the group SO32. Okay? Now I have done it here for simplicity for SO32. But with this construction, you can also do EA cross EA. Okay? And I will not do it because it will take lots of time. Okay? But again, you can do it exercise. It's simple Chinsky, but probably you can do it. I mean, to do EA cross EA, what you have to do is you have these lambdas, which here in the SO32, they go from 1 to 32. But instead, we go to 2 sets. Sorry, but here now A goes from 1. So you take 2 groups of 16 each group. Okay? So now you have on the left side, for the left movers, 16 fermions and other 16 fermions. And what is going to be new? Well, that you have to also consider different Schwarz and Ramon sectors for the two. So you will have even more sectors to consider when you do your mass spectrum. And this will give you then, when you work and those sectors, you will get EA. EA times EA. Wait, one EA from this set of vectors, and another EA from this set of fermions, and another from this set of fermions. But when you compute the states and so on, in the end, they will be like, okay? The degrees of freedom they correspond are this, the gravity sector and this gauge sector, which is just gauge vectors and the supersymmetric factors. Something that I already mentioned is that these are precisely the two groups for which it was known before this construction that the gauge and gravitational anomalies are cancelled. They are not cancelled in the trivial way, they are cancelled by the Green-Schwarz mechanism that is also very special for string theory. But I mean, this will be another thing. So now, what I want to do is to do a compactification of this theory. Okay? And to go from 10 to 4 dimensions. So how do we do that? You have seen in George lectures that you do that by doing spontaneous compactification. By doing compactification, so your space, 10-dimensional space, goes to a 4-dimensional space times a compact 6-dimensional space. Okay. Now, the simplest thing you can imagine is to take this to be a torus, 6-dimensional torus. So what happens if I compactify this on a 6-dimensional torus? I told you yesterday, very basically, that yes, you will get a theory in 4 dimensions, yes. You don't break the gauge group. In general, you don't break the gauge group, and so on. You can find the modes here, the 0 modes, probably you learned in your lectures. And the problem is that you will get too many supersymmetries, okay? Because a torus is completely flat, okay? And if you remember what maybe what you did with George, is that the condition for supersymmetry, when you do the compactification, when you look at the transformations, supersymmetric transformations of those fields, and so on, and you want that the transformations of the fermions are zero, because they will, these are the ones that go to bosons and are non-trivial, and you want them to be zero. And in particular, you have seen that if you want the SUSY transformation of the gravity not to be zero, then you need, in the end, if you look at the internal part, then you need a condition like this, where this is some spin, okay, which is the generator of the supersymmetry. Okay? And this is the condition that you need covariantly constant spinors to have supersymmetry. Okay? But look, for a torus, this is, for a torus, this is here. Okay. There's nothing there. And then this equation is simple to solve. You can tell me the solution. Okay? It's that just eta constant. Okay? So if you had 16 etas to begin, because this is what you have here, say you have 16 supercharges, they will all come to 4 dimensions. Okay? And these are too many. This corresponds, when if you put this 16, if you put this spinor into spinors in 4 dimensions, you get 4. So you get 4 supersymmetries in 4 dimensions. And these are too many, because, well, this is also a long story. In extended supersymmetries, the fermions are not chiral. And in the standard model, we want a chiral fermion. So compactification of T6 is no good. I mean, it's good for other reasons. Maybe good for other reasons. But for phenomenology, it's too simple. Okay? So we need to do something else. And here, this is telling you what you need. You need to kill some of these species. Okay? And this is what I think George tried to explain to. You kill them if your internal space is something else. Okay? In the case, it's a Calabi-Yau. What happens is precisely that you only get one. Instead of having you get one in 4 dimensions. And this is what then reduces the supersymmetry. Now, later I will try to do something with Calabi-Yau using the results, some of the results that you have seen with yours. Here, I will try to do first compactification on orbitals. And just to be simple, I will first explain what orbitals are, and then try to show how, indeed, in 4 dimensions you get only n equals 1 supersymmetry when you do compactification of points. So I will now explain orbitals. Before, I was planning to, I wanted also to connect what I explained to you about the EA cross EA with this fermionic formulation to what Narain did. But this will take me a bit of time. So maybe, but let me mention it before I go to the orbitals. It's also, actually, when you go to the orbitals to work with this fermionic formulation, it's a pain in the neck. Okay, it's really painful. It's almost like multiplying using Roman numbers. So, and for the orbitals, it's much easier to use the bosonic formulation. But since if I start doing details, it will take too much time. I will not do many details in any formulation. So maybe it's better if I can do some basic things instead. Okay. Also, if I go back here, the right will be again, I get the same thing. The left, I get this, but and I don't. One. And a good thing of the bosonic formulation is you don't have to worry about the electrons and Ramon in the left sector. So a nice thing in the bosonic formulation is that the mass formula for the left sector that here involves is in lambda, and you have to do Ramon or electrons. It's much simpler. I mean, it will just be an occupation number for the x's of both types. Okay? And then there is some one half square, where this was a momentum in this lattice. Okay? And here there is a -1, just because this is like a bosonic string, 24. You count, these are 36 plus 8, 24. And this is the usual -1 in the bosonic string that you can exercise, recompute. So this is much simpler. Okay? And this thing now belongs to, it depends. It belongs to, right? I think he called it gamma 60. Okay? And he showed that for modular invariance, this has to be even and self-dual. Okay? And he also told you that there are only two such 16-dimensional lattices. Okay? Now I want to tell you what they are. Okay? So there are two. So this gamma 16. The first one is a set of vectors, 16-dimensional vectors, that can be either of this type or that type, with all integers, or all half integers. Okay, because you sum 1/2 in all. But not only that. I mean, you can, this is something maybe you can check. This even means that all vectors, this vector, the square, has to be an even number. Okay, so if you do n1 square prob, it has to be even. And for this you need that the sum of this and this lattice has a name, spin 32 over Z2, whatever. Okay. It's a 16, it's even and self-dual. To check that it's even, it's easy. To check whether it's self-dual. And the second one is that it's a lattice that is pretty much like this, but the vectors are, I mean, this is actually the product of two 8-dimensional lattices. So the vectors are and divided into groups, and they can be, I mean, it's just easier to read it. So let me call this, I don't know, so the second lattice is the product of two of these. So this is one solution and this is yours. And this is the one that gives you SO32 and this is the one that gives you EN associated. Now here, in this case, this is really, this is the root lattice of EN. all the roots of this group EA are precisely, you have a basis, and using that basis, then you find the vectors are of this form. Okay. Now, here, let's say you want to find the states that are massless, okay, that can match, that can go with the right sectors that are massless. So, okay, now I told you what they are. Okay. These are the ones that have an x equal 1 and b equal 0. And these are ones that will have alphas acting on the vacuum, the alphas for this, that will give you space-time things, and the alphas for this, that give you the Cartan of the field. Okay. But then there are also the things that have an x equals 0 and p squared. Okay. And now the exercise is, given these lattices, you count the ones that have p squared equals 2. Okay? And it's a very simple exercise. So for instance, in the first case, you can see that this can never appear because the smallest one of these has 16 1/2. So the smallest p squared here is 4. So this will never either. That's one reason why SO32 is not very good for phenomenology, because you will never get spin-on representation in the mass. And as I told you yesterday, for instance, in SO2, if you want to have the families of the standard model in SO10, you need a spinor. Okay? So if you don't have spinors, then an SO group is not good for phenomenology. So the only solution will come from here. Okay? And if you count how many of these there are that are not 0, you find the number. And when you sum with the 16 from here, this number gives you 496. I don't want to explain that, but you can check. Okay? You can also do it here. Okay? And here you can see that these ones can appear, because if you put all these to 0, then you have 8 times 8 1/2, and the square is precisely 2. 8 times 1 divided by 4 is 2. So they will be. So in this case, you get spinors. Let's say. In fact, I can say so. This is better for phenomenology, because already one is seeing that there will be spinors in the area. Okay. So you can again count all the states. That might be an exercise. You can count all the states, and you will find the gauge vectors of EA cross EA in a much simpler way. You can also do it with the fermionic, okay? And check that you get EA cross EA in both. But this is then the heterotic in the boson. And also I gave you as a reference the book of Ibáñez and Uranga. This is the they use bosonic, and Polchinski uses fermionic formulation. So you pick your book there. So now I wanted to do orbitals. You have to tell me 10 minutes before the so I wanted to do this orbitals. So what are orbitals? I also want to do orbitals, of course, because I like them, because I worked with them for a long time. But also maybe when we do the brains, some of the things we see here for the orbitals will also be useful when we see, if we ever see the brain construction tomorrow, then it also will be useful. And I think in general, well, it's useful to know about this space. In fact, you have seen already some. So you already know orbitals without knowing. Yeah, so like here, orbitals are quotient spaces. When it's the quotient of a manifold by a group of isometries of a manifold. Okay, what this means that it's not written there. Is that if you have a point in M and a transformation in this gamma, then G, X, and X are the same. So are identified or equivalent in the orbifold. Okay. You have this orbifold. And okay. So you identify points that just differ by a transformation. Okay. So what is the simplest example? The one that you already know. Well, the torus. Okay. The torus, also, Naran has told you everything before. You can see it as the quotient of the plane by a lattice. So what this means is to identify points in the plane, modulo translations in some lattice. Okay. So here is the lattice, the simplest one, simple one, a square one. Okay. So what does it mean to identify points modulo translation? For instance, all these points here in red are identified with all these because I can go to the translation in the lattice. Or all this blue here with this because I can go to the translation. So these are all identified, but this means that I can close here, I can close here, and this is the torus. Okay. So the torus is an orbifold. It's an orbifold that is smooth, that has no singularity. But this is because the translations, the group of translations doesn't have fixed points. Okay. You can also have orbifolds with fixed points. An example is, this is in Spanish, but you have a cone, and here is, you take the quotient by a symmetry, which is just a rotation by 2 pi over n. Okay? So now you will identify this line with this here, and when you close it, you see you get the cone. But now there is this singularity, and this singularity is coming because the origin is fixed on the rotation. So when there are fixed points, there will be a singularity. And the next example of today is the T2 over 7. And let's say here I take again the square lattice. The fancy name for that square lattice is the SO4 root lattice. But this just means square root. And the Z2 is just is generated by this rotation by pi. Okay. And so in this case, you can see exercise. Easy to see that you have 4 fixed points, but the origin is clearly fixed. This is fixed because if you go by pi, you rotate it by pi, you send it here, and then with the lattice translation, you bring it back. Okay? So you can check there are 4 and only 4. And again, because of the identifications and so on, then you identify this side with this side. And then you get the space you get has its representation, okay, with 4 singularities. So again, the fixed points are singularities. So, but this orbifold is pretty much flat. I mean, it's flat except for this singularity. All the curvature is accumulated in this singularity. To begin, this T2, the T2 was flat. Okay. So, but the very nice thing is that even though we have these singularities, it is possible to describe string propagation on these orbitals from using the tools that you have learned. I mean, just using your degrees of freedom on the worksheet. Okay? You can do the quantification of the orbital, even though these singularities are there. And from the field theory point of view, maybe it's complicated because you have the singular space and so on. But from the string point of view, it's very easy. But very after, of course, after you have learned it. But no difficult to learn. And again, here, there's something very powerful at the bottom, and this very powerful thing is modularity. And the point is, well, and also I wanted to say, this is the propagation of strings on orbitals was done in the very first year, 86, 85, by these people. And I just wanted to say that at the time, Dixon was a student. So students have been very important in the development of string theory. And I think you keep with this, I hope you will keep with the tradition. So what they found is that you can do it. You can consider this propagation. But you have to do two things. One, you have to consider the so-called untwisted sector and the so-called twisted sector. Okay? What is the untwisted sector? Well, these are strings, like I've shown here, that they close already on the torus. I mean, they close because they close because they are closed like this, or they close because they wind around one of the cycles of the torus. Like this other green one. Okay, this is closed on the torus because this point and that point are identified. Okay. And so the kind of boundary conditions is just like you would have on a torus. Okay. Now for the twisted sector, what happens is you can, for instance, this string here is also closed. Okay. In the sense that this point here and these are identified by the one of the elements of the group that you are taking the quotient by. Okay? So then if these 2 points are identified by the group, then these things here are also closed. Okay? So there are more things to consider these twisted sectors. Okay? And the point is you have to consider them because of modular values. Okay? Like I was explaining to you yesterday, this would be like language, if you include eventual, you have to include Ramon, because you can do this transformation tau goes to -1 over tau in the partition function. And this will change the boundary conditions. Okay? So you have to do both. And the other condition is the orbifold project one, maybe one, I don't know, one. And this is that in the end, when you want the physical states, they have to be invariant under this condition. And this also comes by modularity. And this projection is similar to the GSO projection. So something you will get, yes, by doing tau plus 1 in the partition. So you can do string propagation using, say, the x's. Yes, I could start doing bosonic string, and this is simple on orbifold. Okay? But then you have to do the two things, include the two types of boundary conditions and do this orbifold projection there. Okay. Yes, so all I will do are the toroidal orbifolds of the simplest type. Okay. So here the torus is the quotient of R6 by some lattice. That is also important. One has to specify the lattice. It's some 6-dimensional lattice. And the set N is it has a generator of order N, and it's in general some matrix in SOC. There's a condition on the lattice is theta, that if I have a vector on the lattice, when I transform it on the theta, it also belongs to the lattice. Now, this theta has order n, so theta to the n is 1. So it must have this kind of eigenvalues. Okay? Where these VIs are like 1 over n, 2 over n. And there are 6 eigenvalues. What is the meaning of these eigenvalues? If I do, if I now take complex coordinates, like this, I take the x's and construct these sets that are complex, plus I here. Then the action of theta on these sets is just the multiplication by faces. Okay? And this is something, trivial. In 2 dimensions, for instance, if you have something like this is a rotation bias. And if you do the action with this matrix, you can do the action on x and y. Okay, but then if you do a set x plus y, then what is the action of this? It would be e to the I alpha set. So this is the same thing. Okay. Same thing. So more precisely, also again one can diagonalize this, and this means one can write it in this way, with this J. These are the Cartan generators of SOC, the ones that commute in SOC. And the reason it's useful to write it like that is because then one knows how it acts on the spinors. And the spinor weights, this also I could explain, it will take time. But I more or less said explain it there. These are just for SO6, this will be 3 vectors. SO6 has 3. So these are 3-dimensional vectors where the entries are plus minus 1/2. Okay? And the action of theta, then because of these are the J's, and if these are the weights, all that these cartans do is to pick up the weights. Okay? So this is the action of theta on the spinors. Okay? And why do I want the action of theta on the spinor? Because I want to look for the conditions of supersymmetry. Okay? So I want to have some supersymmetry, not too many, but also not few. Okay, not 0. So then, if this is going to be invariant, one of them. Okay, these are how many are there? Eight. Okay. And this is 4 plus 4 of SO6. I think George David told you that the spinor of SO6 is 4 plus 4. Okay. So here you have a 4 and a 4. So and I want one of them to be at least one. Okay, this is the condition of SU3 holonomial. That at least one is there. Okay? So, but here we see the condition is that the sum of these numbers has to be even for some combination of the samples. Okay? There is one more condition is that from here we also see it. If we want this theta n to be 1 acting on fermions, spinors, then you need another condition like this. Just take this to the n and you see. So a simple example that we will see is the only one, but these are classified. Okay, there is a complete classification of or solutions, say, of this condition, together with the fact that you need a lattice for theta to act crystallographic. Okay? And this is too much detail that we don't. But maybe I will do just to simplify the story. We can always take this to see, because then both are satisfied without problem. Okay. So one example that we will do is the set 3. And the set 3 you get for B1, B2, B3 put in a vector form. Okay? And then you can tell me which one of these is invalid, or which are the ones that are invalid. Okay? And then you see that there are 2 only. Okay? And they have to have all the same sign. Or, I mean, which is all positive or all negative. This is one spinor inside the 4 of SO6 and one spinor inside the 4 bar. Okay? And then it means n equals 1 supersymmetry in for the by the same arguments that Robert. So this is how we break supersymmetry. Okay, we break the supersymmetry by this action of the theta, by this set n that is acting on the coordinates, and it's necessarily also acting on. Yeah, precisely. I have told you what the action is here, and these are, you can see, these are the right limits, where you also only have x and size. Okay? So now there are also the left movers. In the Fermionic formulation, there are equals. Using these are again some x's, and we know. So for the x's, it will be the same. Yeah, you also have the same thing with the left movers. Bosonic mode. What happens with the lambdas? Well, actually, before I say that, I already told you, I'm going to do the set 3. Okay? I'm going to do the set 3, and here the lattice that allows this crystallographic action is and I will do a set 3, is simple as set 3. It's the product, when the torus is the product of 3 two-dimensional torus. Okay? Now, in each sublattice, the root is the so-called SO3 root lattice. Again, this is a fascinating one. If you don't know root theory, for a lattice where you have these vectors of the same size, these are the bases, and the angle here is 120. And yes, so the set 3 that I think is for you. This corresponds to a rotation by, again, 120 in each sublattice. And yeah, you could consider here and do a nice picture, like for the set 2 that I did before. Also, another exercise you can do is to find the fixed points. Where are the fixed points? Okay, under this argument. And, well, you see, when 5, 3, this, okay? And yeah, you can find the coordinates. And there will be 3 here, 3 here, 3 here. Altogether, this is 27. It's 27 fixed points. Okay, so I was maybe ahead. I told you that you also need an action on the fermions. Well, for the right sector, these fermions, they also have a vector intensity. And so I can also do go to complex coordinates like I did for the x's. The same way, I construct some combinations like this. Okay? And since this is like a vector index, then, for instance, this boundary condition will have again these phases. Okay? And plus the minus and plus, the usual minus and plus of the Schwarz and Ramon. Okay? Notice here, by the way, that for the Ramon, for the Neville-Schwarz, which is where you have this minus, you can absorb this minus in the V by adding 1/2. Okay? This is a useful thing to remember later. Now, what about the fermions in the left sector? Okay, these ones that I call lambda. Okay. That are in the SO16, SO32. I mean, I have 32 of them, and I can construct 16 complex lambdas. That since one is running out of letters and so on, they are called plus minus, lambda plus minus. And this would be for the SO32. For the EA cross EA, they are divided into two groups. And now the point is, again, that by modular invariance, also by studying worksheet symmetries, there must be an action on these fermions as well. With lambda, it is theta of the orbifold has to act also on this. Now how? Well, I mean, it's natural that, again, we realize it with the rotation, with some eigenvalues that have to be multiples of 1/n, because it has to be order 1. And, well, again, since these are fermions, there is this condition that is somehow. So it's convenient to define what is called the gauge shift vector. This little b is like the space-time shift vector, and this is the gauge shift vector. So for EA cross EA, it will be a product of two 8-dimensional vectors, and for SO32, it's a 16-dimensional. And now comes level matching again, or I mean modular invariance again, which one can see as level matching. And that is that, well, level matching, you know level matching, that the left mass and the right mass for L0 and L0 tilde actually equal, the eigenvalues. And this requires this condition, that if I see this as a vector and I see this little b as a vector, like I put it here, then this has to be n times the difference of the squares has to be n. And this comes from modular or level matching, and I will say it more. Now, what I want to stress here is that there is always a solution of this condition. And the solution, and also at the same time, is that you just take this shift vector to be exactly equal to the space-time. Okay? You will have to put the lots of 0, but no problem. It satisfies all conditions. And this is called the standard embedding. This is always there, satisfies all conditions, and so it has a name. It's standard embedding. Okay? Embedding comes from, because you are embedding the action on the space-time on the gauge. That's what it is called. Now, this condition that I said comes from the function. Okay? So, in other words, this will come from looking at the normal ordering constants. Okay? So you have to look at the normal ordering constants and see where this comes from. Okay? So again, I will not explain it completely of lack of time, but I will say there's something I need here and also maybe for tomorrow, which are the mode expansions for this. For this one. Okay? Just like you did for the bosonic string. I mean, how is the oscillator expansion of this? What is the solution of the wave equation now? Okay? So that's a good point about the order that I can solve completely, because this x's, what equation do they satisfy on the worksheet? It's still the wave equation. The only thing that is changing would be the boundary conditions. But to solve the wave equations, well, you already know. It's a sum of something that depends on tau plus sigma plus something that depends on tau minus sigma. Okay? So then one does it. This is. I see already that I'm going too slowly. Yes, and so since this torus I'm saying is the product of three two-dimensional lattices, I will only do it for two. Let's say X4. But just to avoid putting 4, 5, I will just put this in a okay. So what is the okay, then they satisfy the wave equation. Okay. So what will be the expansion of this? Then you know there is a constant term. There is something, I call it tau, the parameter, or T, not confused with the modular parameter, and then there is also here sigma, and then there are the oscillators that I will do later. Okay? So now you go to the theta sector. Okay, in the untwisted sector, you know the solution. On the torus, you can have winding, momentum, and so on. I hope. Now, in the theta sector, the boundary condition is that x of tau sigma plus 2 pi x tau sigma theta, and here some vector that is in this lattice. Okay? So we can now do that. Given this, here we do this. Okay? So exercise for you show that T is 0 and L is true for the set. Okay? Exercise. What happens with this x0? Okay, what will be the equation for x0? See from here. See that x0 is theta x0 plus. Okay. And what is this telling you? Okay. Well, I mean, maybe if I write it like this, then it's clear. Okay. It says if you rotate x0, you come back to x0. Because, I mean, translations in the lattices are keeping the same thing. Okay? So what is this? It says this fixed points. So x0 is a fixed point. And so you can find it. So in this theta sector, you will have these open strings around these fixed points. Okay? Because this we have the set 327 of them for all. So that's the easy part. Now what happens with the oscillators? Well, for the oscillators, then it's better to do this, to work with the complex. Okay? Because now the boundary condition is just the multiplication by a phase. Okay? Not a matrix like here, but it's just e to the 2 pi I. So again, and now again, I want the mode expansion for this. So I know now I start with the constant term. Okay? And then you put the things that depend on tau. This is tau. And since I don't know factors of I, alpha prime, 2, I'm not here. These are the oscillators. Okay? And usually in the bosonic strings, they are integers. Okay? But here we don't know what they are. So I put something that R, I call them R, and it's to be found. Okay?
5 minutes.
5 minutes. Okay. And then I have also the other thing here. So, right movers, left movers. And then I impose which boundary condition I'm going to impose. Well, that set of tau sigma plus 2 pi theta, which is now e to the 2 pi I e sigma plus some vector in the lattice written in the polar coordinates. But the important thing is here. So it's easy to do it. If you substitute. Okay? And what you will find is the following. So again, this, since I don't have time, I mean, it's also, I don't want to board watch this. You find that this is n minus p, but n is an integer now. Okay. And s is n. So what this means is that you will have now oscillators alpha n minus p and alpha tilde n plus p. And you can also do the complex function and so on. But this is already telling you what the creation operators are going to be. So for the creation operators, you look at the negative frequencies. Now you will have creation operators that are like, say, minus from here, or alpha tilde minus 1 p, these are usually less than 1. Okay, like this is 1/3, and what is. And the things with the bar from the set bar. But now point is, I mean, you have this twisted oscillator. So instead of 1, they would be 1/3. And the occupation number you can figure out and so on. Something else you can figure out is now normal ordering. So you need to do normal ordering. Okay, when to put all the negative frequencies to the right, to act on the vacuum, and so you need to do normal ordering. When you do normal ordering, you will have to consider these sums that are not well defined. Okay? But I guess you heard how one regularizes this. Yes. In the case this P0, this is what? is -1/24. No? Using this theta function regularization, or doing some cutoff and so on. Okay? So it's doing theta function regularization. Okay? What happens if you have here? Well, again, this is, I can maybe put it as an exercise. But you can do it also with the cutoff, regularize it with the cutoff, like the pushing in this book, and you get something like this. Or you can, well, there are other ways. And this is the information we need. Okay? So with this, you do the normal ordering for the bosons. Okay? And this is for the real part. But since you have also the complex, you multiply it by 2. Okay? And then once you know it for the bosons, you know it also for the fermions. Because you know that in the Ramon sector, the oscillators are also going to be like, the modules are like for the bosons. Only the normal ordering will change the sign because these are anticoupling. Okay? For the Ramon sector, for the Neve-Schwarz, also, yes, there is the sign change because they are fermions. But also, as I told you, in the Ramon, in the Neve-Schwarz sector, is a minus additional sign in the boundary condition. So you need to shift this by 1/2, and you get the result. Okay? So now one has all the tools, for instance, to check this level matching that I told you. And you can do it as an exercise. Okay? Then you can, if you have, what you have to check, yes, is that the difference between the two normal orderings will give you this condition. In order for this difference to be such that you have massless state for sectors, it's the condition that I wrote. Okay. And this is also what we need to compute the spectrum. Okay. And
I'm sorry. CF is what?
sorry?
CF.
CF. Sorry, where?
On the right hand side.
Exercise.
No. C is equal to CF plus I. So
Sorry, what? Here.
on the right
Yeah.
hand side. The expression of Z.
Expression for C.
The first term.
Here. This one.
Yes, yes.
The fixed point.
The fixed point.
Yeah, the coordinate of the fixed point is going to go to this
Okay.
complex. Okay.
And V is the periodic condition, right?
This one?
V. V. R is equal to.
Yes. I mean, this is this here.
Yes, okay.
Okay. This is the eigenvalue of theta. It would be V1 also. Okay. I'm afraid I have to stop the short, very. Yeah. So I'm going slowly, and then they want to go to sleep and rose. So I will have to run tomorrow. Okay. But also if you have, I don't know, maybe I'm going to slowly. And it's not very interesting. Very interesting. But also the way I'm doing this, I can, since I have 2 minutes. Okay. I mean, one reason I'm doing this is because tomorrow I hope we will see intersecting brains. And when we do intersecting brains, say I have well, schematically two brains that are like this, which means again these are the I'm seeing just it from the image. Okay, and I have here open space. Okay. And what I would like to do is again find the mode expansion for these open streets. Okay, which is something you can do as an exercise. I mean, the exercise is I think it's a simple but good exercise because you first have to tell me what the boundary conditions are. Okay, I mean this is string. It has this coordinate fixed. I mean it's like Dirichlet in this direction and Neumann in this direction. Okay? And here it is Dirichlet in the orthogonal and Neumann along this line. So you can write the boundary conditions for this. Okay? And again, you ask, let me write the mode expansion for this. Okay? And it will be very precisely for this type. So when I come to see this, I will write the solution. Okay? But it's interesting. I mean, what it's telling you is that these open strings between the intersecting branes are like twisted. Okay, so that's one reason I took some time. So maybe if we come so far tomorrow, then you will know them. So I have to stop.
Have time maybe for one quick question. Okay, first I need to apologize, Anamaría, for...
No, Hugo told me that tomorrow I get an additional half an hour.
Ah, okay.